My name is Lula Wang, and I'm a junior at Greenwich High School. My research project this year focused on the development of a novel dual-functioning therapeutic for treatment of acute myeloid leukemia. I became interested in this project following the loss of a loved one, and through this, I realized that over 40% of chemotherapy patients suffer from toxic side effects due to non-selective targeting and immune-evading mechanisms and characteristics of cancer cells. Thus, I engineered and designed a chemoimmunotherapy system to address these issues, which had three main functions. Firstly, my nanocarrier was able to create a bridge between T cells and leukemia cells, therefore forcing and reawakening the immune system. Secondly, it releases interleukin-12, which is a protein that strengthens those T cells. And finally, it delivers a targeted chemotherapy dosage, which triggers apoptosis and also forms memory T cells to prevent cancer recurrence if it were to return in the future. And so I then was able to use FTIR, SEM, and DLS, which were different instruments that were used to highlight the coding progression and additional component of each of my layers in my therapeutic. And so now that I've shown how I created it, I then needed to do multiple different experiments and studies to then test the functionality of each component. And so to start, I did a time and pH release study where I was able to see that my therapeutic was able to release itself within 5 minutes, specifically in the acidic environment of leukemia cells. I then conducted an HPLC analysis, which resulted in the 96% release efficiency and over 100% improvement from current therapies that have a release efficiency of around only 40%. Then, to simulate the immune environment, I added these green fluorescent T cell models to acute myeloid leukemia cancer cells. And then once I added my therapeutic, which are the small red dots over there, I could see how it did form that bridge and did link T cells to the cancer cells, which therefore shows that it's able to reawaken the immune system and therefore take advantage of it to kill the cancer. However, in the non-treated cells, which are shown above that, notice how the T cells had no attraction whatsoever to the cancer cells, showing my nanocarrier's novel and unique ability to take advantage of the immune system. And so now that I've shown you how I did the immune component, I then needed to conduct a study to show the degradation of those cancer cells. And so therefore on the top right, I did a 24-hour in vitro study where I added my therapeutic to acute myeloid leukemia cancer cells, and then throughout those 24 hours, you can notice how the cells began to degrade, and then after the nanocarrier attached, and completely degraded after 24 hours. And so the final study I did was a cell viability assay, and then that top graph with the blue and the red that you can see, I showed that while normal and standard chemotherapy resulted in only 36% cell deaths, my therapeutic resulted in a 94% cell death rate, nearly a 3-fold improvement from standard chemotherapy. Thank you for listening, and I'd be happy to answer any questions.
Amazing job, Lula. Do we have any questions in the audience?
Hi, I was just wondering if this treatment is used as a replacement for chemotherapy or alongside chemotherapy.
Yeah, of course, great question. So this therapeutic that I created would definitely be a replacement for standard chemotherapy. While it does contain chemotherapy, it's only one component, but what my therapeutic does, which is unique and different from current chemotherapy, is that it combines it with an immunotherapy component. And then through that, it's able to prevent relapse if those cancer patients get cancer again, which is a common thing to happen. And then it also takes advantage of that immune system so that you can take lower dosages of chemotherapy, preventing that toxicity seen right now in the status quo.
Thank you for the presentation. I was wondering how you designed the model for the test.
Yeah, of course. So to design this model, I had to create artificial or T-cell models because I didn't have access to live animal models due to my age and also regulatory constraints. And so to do that, I used one of the proteins that is found on T cells that my therapeutic targeted, which was CD3. And then I added that protein to the solution, which was then able to create these vesicles that modeled the membranes of T cells. And then once I added those to actual cancer cells, I could see how those were able to attach to the cancer cells. showing how those T cell models and showing that my therapeutic did have specificity to both T cells but also to leukemia cells.
Any other questions?
Good. Let's give another round of applause for Lula. Next up, we have Nish.